Right, ladies and gentlemen, good morning. We are continuing with lecture number 4 of the year 2016. It's based on the textbook of Cengel and Ghajar as a framework. We have started with chapter 4 on transient heat conduction. We've spent the first lecture on getting an idea where this chapter fits into all the other heat transfer material. We looked at applications, why it is important, and we've ended with the most important result, and that is that the temperature is a function of time. There are many problems like that. All problems in industry and life is not steady state problems. There are ones where we have changes as a function of time, and we need to figure out how can we handle that. Well, I've showed to you that there are different approaches that we can follow, from very simple, and then it will become more complex, up to a numerical technique where we can, for example, solve a problem with computational fluid dynamics. With the previous 2 lectures, we've spent some time on the lumped system approach, and very specifically, we've spent a lot of time where I've showed you what the limitations is of the lumped system approach, how it can be identified, and what rule of thumb we typically can use as a good guideline to assist us in when we should use the lumped system approach or not. However, the one thing that is always very important to remember is that with the lumped system approach, we get a temperature. And that temperature for the body is the temperature everywhere, on the surface and the center, etc. So it is, in many cases, maybe a first good order approximation. The next phase of transient heat transfer is now more complex, and you'll already see it with all the mathematics and the results. We have identified 3 different geometries, which occurs a lot, and we've applied the energy equation to it, and we have derived a solution. And this solution is given here, and that is the solution for a large plane wall. Okay. Then, so that is the solution, and sorry, I forgot. Part of the solution is that lambda ton multiplied by the Biot number is equal to, is equal to the Biot. Lambda n ton, lambda, like that, is equal to the Biot number. Okay. Now the first thing, now all of you, you have to remember you have to be very careful. In the study guide, I've given you a list of all the errors we know of in this textbook. Okay? I hope that you've downloaded it and that you've corrected your textbook, because remember, you're going to use your textbook in the exam and in the tests. And if there are errors in the textbook, you're going to have errors in your papers. Now last year, for example, not last year, but the previous edition, edition 4, there is, for example, a 5 in here, which should be removed, obviously. So I know that there are some of you who are using the previous edition, so please make sure that you've made that correction, and all the other corrections relevant to your textbook. Okay. So that is the solution for the large plane wall. But then I've also told you there's a solution for the long cylinder, and there's also a similar solution for a sphere. More complex, of course, in terms of the mathematics, but the results are all summarized in table 4.1. So let's look at table 4.1. Marlies, if you can zoom for me on table 4.1. There's all the results, okay? And you can look at it and you could say, yes, okay, great, I understand it, I will be able to use it in the tests and exams. But there are quite a number of hidden things in it, which is very, very important, that I would like to highlight to you. The first is, I've mentioned previously to you, the fine print. Okay. So you will see at the bottom of the table, it says, for example, here, theta is how the temperature, the non-dimensionalized temperature, is defined. You see it? Then it also tells you how the Biot number is defined, as well as the Fourier number. Okay. So everything is there, you don't have to remember it. But you have to know where it is, and you have to know when to apply it. So with the second solution for a cylinder, what is different from that solution from that of a plain wall is what? You'll see two J's there. Okay. Now those J's are the solutions of a Bessel function. We've done that also in mathematics. So it is just part of the procedure of trying to get a solution out for this problem. And those can be found in table 4.3. So if you look in table 4.3, okay, so for example, let's use eta is equal to 1.5. Then the first value for J0 is equal to what? 0.5118. Okay? And then there's another value for J1. Okay, do you see that? Okay, let's just go back to the equations again. You go back to the equations, you'll see that it says there in the equation J0, okay, and then in brackets there's lambda n multiplied by r divided by r0. Okay, so this is the value of eta. So if you calculate it and it is equal to 1.5, you can go and get the Bessel functions. You see? So it's very simple to use. Then in the third solution, that for the sphere, come on, if you can go back to that one again. So with the third solution for the sphere, there we see also the temperature distribution, but in this case we do not see any Bessel functions. So it is only with the cylinder. Okay, so 3 sets of equations all tabled for us and summarized in table 4.1. Now, the thing is with this is, as you can see, it is an infinite series. Okay, so lots of calculations. That is our first reaction. Now these days with a computer it's very easy to calculate, but previously, before computers, engineers and scientists were much more critical about mathematics. These days we just put in the equation. Okay. They were much more critical about it, and it made them very wise, because it would take days and days and days to do a calculation like this. So a lot of effort would go into the calculation of it. So for that reason they were more critical to identify certain things which are very important. So for example, let's look at a case. Let's call it a critical evaluation. Just as an example, let's look at the case of the Biot number of equal to 5, the non-dimensionalized length equal to 1, and t equal to 0.2. Now with that, with the Biot number known, let's suppose it is a plane wall, with the Biot number known, we can get the roots. Okay, where do we get the roots? We get the roots in table 4.2. Okay, Marlies, if we can go to table 4.2 quickly. There's table 4.2. Do you see them? Everything summarized for us. And you will see on the left we've got the Biot number, and then there are 3 pairs of columns. The first one is for the plane wall, the second one for the cylinder, and the third one for the sphere. Now what I would like to recommend is that next to lambda 1 and lambda 1, you put in brackets radians, because it's not degrees, it's in radians. And it is also one of the errors that has been identified in the textbook that has been brought to your attention. So I would recommend that you correct your textbook in that regard. Okay. So next to lambda 1 and lambda 1, in table 4.2, put in brackets rad. It's for radians, it's not degrees. Okay. So for in this case, let's suppose, as we see the Biot number is equal to 5, okay, then we can see lambda 1 is equal to 1.3138 for a plane wall. You see that? And next to it is the A1 value. However, just take note that these are just the first values. That is for n equal 1. Because there's an infinite series, because Tom is repeating every pi. Okay. But if we now look at that, and we look at n, and lambda n, and an, and theta n. And let's go and do this calculation for n equal 1, 2, 3, 4, and 5, etc. Okay. For n equal 1, it would be equal to 1.3138. Okay. A1 is equal to 1.2402. Do you agree? From the table. Okay. And then with that known, we can put it into this equation, okay, and we can calculate theta, which is equal to 0.22321. Okay. Now we would like to do it for n equal to 2. Now for n equal to 2, lambda n is not again equal to 1.3 because it moves on the x-axis. Okay. So that would be equal to 4.0336. So I think it is that plus pi, something like that. It always goes further away on the x-axis. And the an value would be equal to 0.3442, and then theta would be equal to 0.00835. Okay, now let me show you the other values if we would do it for n equal to 1, 2, 3, 4, and 5. So Marlies, you can show it for us quickly. Okay. There they would be. Okay. So, what do we observe if we now look at it very critically, and especially if you're a little bit lazy like me, and you do not want to do lots and lots of calculations? The results is actually obvious, because it means that the final solution theta is equal to theta 1 plus 2 plus 3, etc. All of them. Do you agree? Okay. And the first one is equal to 0.22321. The second one is equal to 0.00835. The third one, I think 401, etc. Okay. So as you can see, the results are just getting smaller and smaller. And if we just would go and add all of them, it would end up in 0.3145 if you're going to do it for many. Okay. So if we now compare these results to the first term only, what do we see? Okay. We will see that the first term in some cases would be sufficient. Now the question is, well, when is sufficient now? How must I now know? You have to go and do it every time. Well, not really. I think if you go and do many of these calculations, they have found that if tau is typically larger than 0.2, if tau is larger than 0.2, then the error would be smaller than 2% if you only use the first term. Okay. So, therefore, it would then mean that is a good guideline for us. It's not a rule, okay? It's not a law. But if we now get an object, such as a long plane wall, a cylinder, or a sphere, and we want to do transient heat transfer calculations on it, and we check the tau, and it's larger than 0.2, then we know that we only have to do the first term. Okay. Now the result of that is that that equation now, for the first term, we can write in the following format. Marlies, if you can go to the equations now for us. There they are. Okay. So for the plane wall, the one-term approximation, those three equations there at the top, you'll see them. For plane wall, there's the temperature distribution for a wall. Again, on the right, it indicates for tau larger than 0.2. Okay, so we only use the first term. Now, the second thing that is also important is that in some cases, x is equal to 0. And if x is equal to 0, sorry, Marlies, if you can just show here again on the equation. So if we look at this original equation, So for some cases where x is equal to 0, when is x equal to 0? X would be equal to 0 on the center line, because that is where x starts. So x is equal to 0. So that temperature there we call theta 0 at the center. Now at least if you can look at the equations again for us. So for those special cases, at the center we have equations 4, 26, 27 and 28. I don't think that is the numbers in your textbook. I'm not sure if it's exactly the same. It might be the numbers of the previous textbook, but those are the three equations there. So now they are much simpler. Do you see? Okay. Right. So lots of mathematics, but the last thing that we should look at, I think, before we start with calculations is that in this and in the table they refer to the Fourier number. The Fourier number, we call it tau, in some cases f0. The Fourier number is given, but what does the Fourier number mean? The Fourier number is equal to typically alpha multiplied by tau, alpha multiplied by the time divided by L squared. And if we analyze it, and we don't have enough time for that, that would mean it is the ratio of the conduction heat transfer by the ratio of which the heat transfer can be stored or released in the body. So how quickly the heat can come in and how quickly it can come out. So the Cp there comes out, and that Cp is actually then that alpha. You remember? It is in that term there. Okay, so that is what the Fourier number means. Let's do an application of all these equations so that we can now feel a little bit more at ease with all the mathematics that we've derived. But before we start, I see there are here and there somebody talking to each other and looking very worried. Any questions before we continue? Yep.
Sorry, I cannot see what it says. It says if you conduct.
Okay, the conduction heat transfer by the heat transfer rate stored. What you store, okay, storage. Okay. Any other questions before we continue? Good. I don't know if how many of you are looking at these series on TV about NCIS and CSI and forensic science and stuff like that. So let's do an application like that, a dead body, okay, a dead body. So a dead body is found, okay, and the question is always, when did the person die? Okay, when did the person die? What do? They take a thermometer, a long one, and they would put it into the body. I think normally they would put it into the liver, and they would measure sort of almost the center temperature inside the body. Okay. Now, in this case, that center temperature at the center was found to be 25 degrees Celsius, and that was at 1700 hours when the test was done. So the body temperature is 25 degrees Celsius. Okay. So the question is, when was the person killed? Okay. So when did he die? Okay. So let's make a few assumptions to see if we can solve this problem. The first one is, if we now look at the body and we look at all the mathematics and all the stuff that we've done so far, I think there are two possibilities, isn't it? We can say, well, let's go and do a lump system approach and calculate the temperature, the time. Or maybe, can we look at all this complicated mathematics and use any of that? And maybe after some thinking about it, you would say, well, okay, maybe we can assume that the body is a cylinder. Oh, sorry, not that one, a plain wall, a cylinder. Okay, do you agree? Cylinder, okay. So, let's suppose it's a cylinder. And looking at this person, we would say approximate height of 1.7 meters and approximate diameter of 300 millimeters on average. And from asking some questions, the people who investigating this found that the person wasn't sick or anything like that. So it would mean that most probably the initial temperature was 37 degrees Celsius, because that is most normal people have a temperature of 37 degrees Celsius. Do you agree? Okay. Now, the body has been found in a storeroom. There's no ventilation. So you as an engineer would say, well, if it is natural convection, the transfer coefficients are approximately in the order of 10, okay? But that would be in most rooms. In this case, there's no ventilation, so you would say, well, let me go for the heat transfer coefficient of about 8 watts per square meter degrees Celsius. And you would go and measure the temperature, and the average temperature is about 20 degrees Celsius during this period. So no fluctuations in the temperature, approximately 20 degrees Celsius. Okay. Now, if you think back about the lump system approach and also this approach, you will remember there are things which are important which are being used in the calculations, things like the thermal conductivity, the CP and stuff like that. So we will need that for this body. So who of you know where we can get that? What would you suggest?
Assume the CPs of water.
Yes, exactly. So about 80% of your body is water. So since there is not in your tables, as far as I know, values for the human body, let's start with water. Right. So we're going to say, let's assume water. Now, I want you to go and look in your tables for me, and that is why I say it is important that you bring your textbooks with me. You will find that the properties for water is in table A9. Okay, now let's start maybe with the thermal conductivity. Who can give me the thermal conductivity of water? Thermal conductivity of water. In table A9, do you get it? What is the challenge that you have now? At which temperature? So that is now the first challenge that we have. Okay, so what we normally do is we choose a temperature at what we call the bulk temperature. The bulk temperature is sort of an average temperature that we predict. And in this case, we would say, well, the initial temperature plus the temperature at 1700 hours, okay, divided by 2. Let's use the properties at approximately that average temperature. So that would be equal to 37 plus 25 divided by 2, which means that we have to go and get the properties for water at 31 degrees Celsius. Okay. Now let's suppose, okay, no, we will address that later. Okay, so now at 31 degrees Celsius you can get the properties. Okay, so and the properties would be equal to 0.617 watts per meter Kelvin. It would be rho is equal to 1,000 kilograms per cubic meters. CP is equal to 4178 joules per kilogram degrees Celsius. And alpha, the thermal diffusivity, which is equal to K divided by rho Cp, you can calculate it from here, you can get it in the textbook, is equal to 1.477 multiplied by 10 to the minus 7 square meters per second. So that's the properties of water at average temperature of 31 degrees Celsius. So it's the average between when the person died and when it was found. So just as an exercise, what we're going to do now is we are going to use the lump system approach to calculate and determine the time of death, and then we're going to do it more accurately, and then we can compare the two approaches. Okay. So let's do the first one with the lump system approach. With the lump system, can I clean this? Is it anybody busy here? Fine? Okay. So with a lump system approach, Okay, now with the lump system approach, we have to calculate the characteristic length because we're going to need that in the Biot number. The characteristic length is the volume divided by the surface area. Okay. What is the volume of the body? The volume of the body would be equal to pi divided by 4d squared. Pi divided by 4d squared would be this area multiplied by the length of the body. Okay, you agree? Okay. And if you go and do the substitution of that value, then it would be equal to 0.1202 cubic meters. Okay. Divided by the surface area of the body. What is the surface area of the body? Well, the first surface area is this one here on the outside. Okay, which is equal to pi divided by d multiplied by L. Pi multiplied by d multiplied by L. You agree? It's the outside surface. Okay. But then we have this surface area here that we can also take into consideration, and that would be equal to pi divided by 4d squared. However, we have two of them. We've got one on this side and we've got one on that side. So it's 2 times pi divided by 4d squared. Is that fine? Okay. So if we go and calculate that, then it is 1.744 square meters. Okay. Now we can go and calculate the characteristic length, and that is equal to 0.0689 meters. Okay, any questions? Nothing. Right, let's go and calculate the Biot number. The Biot number is equal to the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity. Okay. Now remember, we've discussed this. We've said that the lump system approach would work well if the ratio of thermal conductivity to thermal resistance, the resistance of conduction inside the body divided by the resistance of convection is very small, typically about less than 10%, so Biot number less than 0.1, and that would be when the heat transfer coefficient is low. In this case it is that would be small, well, 68 millimeters, so it is, I don't know, is that small or large? We don't know. And K should be large, okay, good conductivity. In this case, we've got water, K of 0.6. K for copper is about 260. So we immediately see thermal conductivity is very low. Okay, but let's go through the calculation in any case. So the heat transfer coefficient is 8. The characteristic length is equal to 0.0689. Divided by the thermal conductivity is equal to 0.617, and that gives us a Biot number of 0.89. Okay, so the Biot number is larger than 0.1. Okay, so therefore, larger than 0.1, sorry, okay, and therefore not to be used. So the lump system approach shouldn't be used in this case. Okay, but let's use it in any case. Just go and check what is going to happen. Okay, so the non-dimensionalized temperature for the lump system approach is equal to the temperature minus T infinite divided by Ti minus T infinite, and that is equal to e to the minus bt, okay, where b is equal to the heat transfer coefficient multiplied by the surface area divided by rho, the volume, and Cp. Okay. So let's calculate b while we've got it here. It's equal to 8. The heat transfer coefficient multiplied by the surface area, 1.744. Divided by the density of the water, which is 1,000, the volume, which is equal to 0.1202, and then multiplied by Cp, which is 4178. And the result is that B is equal to 2.778 multiplied by 10 to the minus 5 per second. Okay. So we've calculated B. Okay, and let's call that equation 1. And let's say, let's go and put this into 1. The temperature, what would the temperature T be? Remember, this is the temperature at time T. That's the temperature when the body was found. Okay, oh, sorry, that was the temperature originally. So we want to know when the person was killed. Okay, so that, no, sorry, I'm talking nonsense, sorry. I'm confusing myself now. Okay, so we've got that. So that is the temperature at T. Okay, and that is T. Okay, and that was obviously then at 1700 hours. Okay, so what was the temperature at 1700 hours? It was 25. You agree? Okay, minus the environment temperature is 20. Okay, divided by the initial temperature of the body, that would be Ti, and that would be when T is equal to 0. Okay. When T is equal to 0, the temperature was 37. Minus the environment temperature, which is 20. And that is equal to E to the minus 2.778 multiplied by 10 to the minus 5 multiplied by T. Okay. Therefore, we can solve the time T as 44,047 seconds, which means it is approximately 12.24 hours ago. Okay. So, 1700 hours minus 12.24 hours, and it would mean that that would be approximately 4 o'clock in the morning and 46 minutes. Okay. Do you agree? Any questions? Yep.
Are we allowed to round off the density of water? Because in the textbook it was 996.
It's a good question. Rounding off, if you think of density 996 in comparison with 1,000, I would also use 1,000 because, I mean, it is such a small error if you would use 996. Yeah. Is it actually 996?
More or less.
More or less. I was a little bit lazy. Okay, question?
Sorry, sir. You said the lump sum approach wasn't supposed to be used.
Yes.
Because the value was small. We used it anyway.
Yes.
So is that value correct now, or
well,
we need to do another approach?
Yes. Remember, what I've tried to show to you with the Beard approach is there's absolutely no law in the world telling you the Beard number must be 0.1. It is always an engineering discretion, okay, of that ratio of the resistance. So in this case, with the Beard number 0.89, what does it mean? It means that the resistance inside the body is approximately the same as that of convection. So it would mean for me as an engineer, I should be careful. Okay, but it's a first order of magnitude calculation. Most probably, and we will see later on, most probably it will not be out with a factor of a 10 or 100. Okay, in many cases you just want a first order calculation, and then this can help. Okay, right, now let's do it the right way. And we start then with table 4.2. I want to refer you to table 4.2. Okay, now let's look at table 4.2 again. Okay, sorry, let's first just look at the slide of all the excuse me, approximations that can be used. Okay, now the first thing is that remember, what is asked for us is the time. Okay, and time and tau is actually connected. So if we just come back here to the Fourier number, Okay, that is the Fourier number. And in table 4.1, that is the exact solutions, but then we've got the solutions for tau larger than 0.2, okay, which is the simpler ones. So at this stage, we do not know if tau is 0.2. But what we're going to do is we're going to say, let me assume it and do the calculation, and then I can check. Okay, so that's what we're going to do. Because remember, the temperature was measured here in the center of the body, 25 degrees Celsius. So it can make things much easier for us in terms of our equations. So if we now go and look in table 4.2, sorry, this time I'm going to table 4.2, not least. Table 4.2 for the Biot number, for a cylinder, and also look in your textbooks and see if you agree with me. And the Biot number is equal to 0.89, so about 0.9, okay, approximately. And then lambda 1 would be equal to 1.2048, and A1 would be equal to 1.1902. Do you agree? Okay, so tau larger than 0.2 we assume, and we say we will check it later. Okay, now for a cylinder where we need the temperature in the center, theta 0, the equation that has been derived is the temperature at 0 minus T infinite is equal to the inside temperature, the initial temperature minus T infinite, and that is equal to A1 e to the minus lambda 1 square multiplied by tau. Okay? So you see how easy it is now to do the calculation. So the temperature in the center is 25. The environment temperature is 20. The initial temperature was 37. The environment temperature 20 is equal to A1, and A1 is equal to 1.2048 e to the minus lambda 1.2048 square multiplied by tau. I'm going to, yep. Sorry, okay, A1, okay. Sorry, did I write it? Is it here? So it is 1.1902 E. Is that right? Okay. And from that, we can get tau, which is then equal to 0.963, which is great, okay, because it's now larger than 0.2. Okay. And tau is equal to 0.963, and that is equal to alpha t divided by the radius square. So 0.963 is equal to alpha, which is equal to 1.477 multiplied by 10 to the minus 7 multiplied by t divided by the radius of the body, and that would be 150 millimeters, 0.15 squared. And from this we can get the time as 146.727 seconds, and that is 41 hours. So it's more than 3 days. Well, in the previous approach, it was a little bit more than 12 hours. Okay, so we can immediately see the difference between the two approaches. But at least it is not a factor of 10 or 20 or 100 out. Do you all agree with me, ladies and gentlemen? Are you happy? I'm not happy at all. I've trapped all of you. It's not correct. What did I do? It's incorrect. Do you remember yesterday I told you about the characteristic length and the calculation of the Biot number? Do you remember? We have used now this Biot number that we have calculated here. Where is it? 0.89. In here we've used the Biot number for the lump system approach, and that is incorrect. Marlies, can we go to table 4.1 again quickly? The fine print. You see in the fine print, what does it say? How should the Biot number have been calculated? The Biot number should have been calculated as the heat transfer coefficient multiplied by the radius divided by the thermal conductivity, not the characteristic length. The characteristic length is for the lump system approach. Very important. I've showed you that yesterday. You remember? Right. So, let's see what difference it makes in our calculations. So the heat transfer coefficient is 8. The radius is equal to 150 millimeters, 0.15 meters, divided by the thermal conductivity, 0.617, and now the Biot number is equal to 1.944. So I cannot repeat how important it is. So do not use the characteristic length calculated from the volume divided by the area. This is for the lump system approach. You can only use it for that. Okay. Right, now that we have the Biot number, for a Biot number of 1.9, let's look at the table again. What is the Biot number equal to? 1.9, it's approximately 2. You can go and do the exact calculation. But if I look at lambda 1 quickly, it is about 1.07. You agree? No, goodness, remember, I keep on trapping you today. You have to look, that is for the plane wall. Look, there's a plane wall, cylinder, and a sphere. So we have to look for the values for the cylinder, not the plane wall. You see? So for the plane wall, for the cylinder, very important, lambda 1 would be equal to 1.5995, and A1 would be equal to 1.3384. So it just shows you how easy these calculations are actually, if you understand how to use them and how you can use the table. Okay. So for a cylinder, we want the temperature in the center. That is why we use the O there. The non-dimensionalized temperature is T0 minus T infinite divided by Ti minus T infinite, and that is equal to A1 e to the minus lambda 1 square multiplied by tau. That's the equation. It is a simplified equation of table 4.1 where R is equal to 0, so the cost term disappears. And secondly, we make the assumption again, okay, assuming again that tau is larger than 0.2, so that we can only have to calculate the first term and not all the other terms of the series. So if we now go and do the substitution, the temperature in the zero was in the center was 25 degrees Celsius. Okay, the environment temperature was 20. the initial temperature was 37, again minus 20. The environment temperature is equal to 1.3384 e to the minus 1.5995 square multiplied by tau. Just go and put in the value of A1 and lambda, and then we can calculate tau as 0.6466. Okay, so, well, it is larger than 0.2. Okay, so we are fine with the first term approach, and that tau is equal to alpha t divided by R0 square. So it is equal to 0.6466 is equal to, alpha is equal to 1.477 multiplied by 10 to the minus 7 multiplied by t divided by the radius, which is equal to 150 millimeters. Okay. Do you all follow? You all happy with the results? Okay. Yep.
For the real number of 1.5,
yep.
should you interpolate your...
Yes, if it's not, if I didn't use 2, then it is because I've used an interpolation. No. No, I don't think I've did an interpolation, I've solved it.
So you can interpolate to get your values?
Yes, you can, but yeah. Yes, you can, but in the test or exam, I wouldn't recommend that you spend time on that. I will be happy if you interpolate. That is a general statement. Remember, if I say that, I'm going to show you later on when you cannot do it. So as an engineer, you always have to be careful. So, okay, let me spend time on that. If you look at the values of between 1.9, between, let's say, 2 and 3, you'll see that in general, the values are actually quite close to each other, okay? And therefore interpolation is fine. Or you can just sort of select the nearest one, okay? But if they are far away from each other, then you have to be careful and maybe you have to go and solve the equation, okay? Right, so the time is then equal to 98,000 minutes, 517, and that is 27.37 hours. Ago. Any questions, ladies and gentlemen? If not, thank you very much, and then I'll see you again next week. Bye-bye.